We're going to work more with parametric equations today, and we're going to talk about eliminating the parameter. So in the last lesson, we saw where some parametric equations can't be considered functions because they won't pass the vertical line test. Although parametrically they are functions, because the independent variable does not lead to repeated dependent variable outputs, which would fail a so-called vertical line test in the rectangular coordinate system. This isn't true of all parametric equations. Many have an equivalent rectangular equation function, and we can find these by a process called eliminating the parameter, where we can eliminate the parameter altogether and find an equivalent rectangular equation that would give us the same graph in the plane. So let's practice that. Here we are given this set of parametric equations: x equals the square roots of the quantity 2t and y equals 4t, and our t values must be greater than or equal to 0. And we want to eliminate the parameter. So here's the process. We're going to solve one of these for the parameter t. It doesn't matter which. I can put t in terms of x, or I can put t in terms of y. It doesn't matter. I'm going to take one of these equations and solve it for t equal the other variable. Then I'm going to take that and substitute it in for t in the other equation. So let's see what that looks like. All right, so we have x squared equals 2t. And this, by the way, is the graph of this parametric function. So it looks like a parabola that opens up. It's going in this direction as t gets larger. So I'm going to take this parametric equation and I'm going to solve it for t. So I square both sides and I get x squared equals 2t, and then I'm going to divide both sides by 2, so I get t equals x squared over 2. Now that's step one. Solve for the parameter t in one of the equations and then substitute that in for the t value in the other equation. So I'm going to go back to y equals 4 times t and substitute in that value for t. So y would have to equal 4 times x squared over 2, and that cleans up to y equals 2x squared. So let's graph that and let's see if it looks familiar. And sure enough, it does. It is the exact same equation, because this set of parametric equations doesn't fail a vertical line test. Therefore, it is one that we could eliminate the parameter on. So you can see, even though we don't really consider in the red graph direction, and we do consider in the blue graph, because it's parametric, we consider direction, it's still the graph of the same function, as it should be when we eliminate the parameter. So let's look at another set, and let's follow our two-step process here. We want to find a rectangular equation equivalent to this set of parametric functions. So x equals t squared, y equals t minus 1, and t, the domain of this function, is -1 to +4, inclusive of those endpoints. So that's going to play a role when we actually find the equivalent rectangular equation. Since the original t parameters are limited in the domain, that may well limit our x parameters in the domain for a rectangular function. So let's pick one of these and put t in terms of one of the variables. So here we're going to go in the other direction. Let's put t in terms of y. So here all I have to do is add 1 to both sides, and t is going to equal y plus 1. Then the next step is I'm going to substitute that value of t into the other equation. So therefore, x, since it's t squared, would have to equal the quantity y plus 1 squared. So now we've done that. We have found the rectangular equation that's equivalent to these parametric equations. But we do need to consider, if we are told that there is a domain to our parametric function, we need to find the domain to the equivalent rectangular function. So we're going to calculate the restrictions. Since t has to lie between -1 and 4, x would therefore have to lie between -1 squared and 4 squared. But here's the problem with putting negative values into this squared function. The reason that this left endpoint is 0 is because I can't put a value into t squared and get a negative value. And there are values of t between 0 and +1 that need to be included in my x domain. So I know that may sound a little clunky, and I wouldn't obsess about it, but we can practice this if it becomes an issue. But we do need to consider the fact that normally what we do is just say, okay, well, x behaves this way, so I'm going to do this value here. I'm going to plug it in for t, and I'm going to plug this value in for t, and x has to be everything in between. But because t is a negative value and x is only going to give us positive outputs, we have to pay attention to that. Y is a little more straightforward. Here, y is t minus 1, so I'm going to plug this value in for t, that gives me -2, and I'm going to plug this value in for t, and that gives me 3. So y is much more straightforward. So I would have x values between 0 and 16, and y values between -2 and 3. So since we are talking about x values here, it's a rectangular equation. X is our independent variable. There's the domain of our function. This would be the range of this rectangular function. So don't worry about this part of it as much as being able to eliminate the parameter. Let's try it one more time. Here we have angle measures. Now sometimes they'll use theta. We could equivalently be looking at x equals the cosine of theta, y equals the sine of theta, where theta lies between 0 and 2 pi. Here they still use t, so it doesn't matter what variable you use as your parameter. Here we'll stick with t. So our x coordinate is found by taking t values starting at 0 and going up to 2 pi and plugging those values into the cosine function. And our y coordinates are found by doing the same thing with the sine function. We shouldn't really be surprised that that's going to lead us to a circle, because when we plug in values between 0 and 2 pi into the cosine function, those values are going to be on the surface of the unit circle, the x coordinates are, and the y coordinates are as well. So it is the angle on the unit circle that we're talking about. So the graph of this is indeed a unit circle. We do pay attention to the arrows. T is getting larger as we go around the unit circle, so we shouldn't be surprised that it's a positive angle direction, right, which is counterclockwise. So if we want to eliminate the parameter here, we have to go back and remember some things from trigonometry. We remember that sine squared of t plus cosine squared of t equals 1. That was the Pythagorean identity. And since x equals cosine, then I get to call that x squared. And since y equals sine, I get to call that y squared. And again, hopefully you recognize now after our conic section work that that is just the equation of a circle centered at 0 with a radius of 1. So eliminating the parameter in this way is a little bit different than what the process that we just did a while ago, which is take one, solve it for t, substitute that into the other one. That's not going to help us when these trig functions show up. We have to go back and heavily rely on what we know from trig. And the Pythagorean identity shows up a lot when we do this. All right, so let's look one more. Here we have x equals 2 cosine of t and y equals 4 sine of t. Again, we're within one revolution around the point of origin, and we're going to go back to our Pythagorean identity work. We're going to go right back to sine squared plus cosine squared equals 1. So when we want to eliminate the parameter on trig functions, then it doesn't help us to solve one for t and use the inverse functions. We go straight to the Pythagorean identity. And if y equals 4 times the sine of t, then in order to be able to plug that in here, I have to solve this for the sine of t. So I have to recognize that the sine of t equals y over 4, and I have to recognize that the cosine of t equals x over 2. So that's what this work here looks like. So the sine of t is y over 4, the cosine of t is x over 2. Now I can plug those into the equivalent of the Pythagorean identity, and clearly, hopefully you can see now we have the equation for an ellipse. So this is in a circle, this is an ellipse. So there we go. Very straightforward. So eliminating the parameter, not only when we can go directly to a rectangular formula with that two-step process of solving one and putting it in terms of one variable and substituting into the other, that's one technique we can use. But if trig functions show up, we need to recognize and remember that we can use the Pythagorean identity and still change a parametric set of equations into an equivalent rectangular form. So there we go. Come to class next time and we'll practice eliminating the parameter.